The OSSAT program, we're aiming to develop an open source platform which can be used to service a wide range of space applications. We're hoping to make space more accessible by driving down the price point associated with traditional satellite and small satellite systems, but whilst maintaining the level of performance so that it can be offered as a solution more capable than a CubeSat. So this will be a modular platform capable of servicing missions anywhere in the 25 to 250 kilogram range. And as some of you will no doubt have heard us say before, we consider that the platform a bit of a parasite on the mission, as it is really the payload which you want in space. So a major aim of the open source satellite program is to maximize that payload mass fraction and available volume by reducing the size of the platform as much as possible, aiming for an integrated sort of platform solution as we head towards a utopian solution, I suppose, of a platform on a chip design. So to go from that blank piece of paper all the way through to a physical architecture for the platform, we've decided on an approach which splits the work into a number of distinct phases, each with a clear set of objectives and associated with review. So the first of these was the kickoff phase, and the key outputs of this stage were to identify what the problem is and provide rationale for the top level objectives that we've set for the program. We also derived a top level plan, so we could have a schedule that would manage the completion of the various activities that would be undertaken as part of the approach. So on completion of the kickoff phase, which provided our plan for how to proceed with the program and its top level objectives, the external inputs phase began. And as has already been stated, we intend the OSSAT platform to be capable of servicing a wide range of applications. And although our team has a lot of experience in designing, building and operating satellites for different applications, we haven't covered them all. So therefore, at this stage, some research was required to identify what the possible applications of space are. And an intern working on the OSSAT program over the summer produced a great piece of work identifying as many of the applications of space as possible. Now, I think she came up with a list of applications that extended into even the hundreds. So these had to be distilled down into those that we deemed cover most of that market share. And this was also conducted by considering the roadmap we have for the open source satellite, whereby the first variant will service a modest low Earth orbit missions in benign radiation environments. And with development, we will move towards being able to operate in medium Earth orbits and geostationary Earth orbits and possibly beyond. So this table gives you some examples of the applications we have selected that will be used to drive the design of our platform architecture. So those applications that we think cover the majority of the market share. We also have other categories of applications, including those that we think should still be covered by the initial design, but won't be used to drive that architecture. But also from this vast initial list, there are also those applications which we are considering as outliers in the market and will therefore not be covered by the initial platform. Although we believe that the majority of payload types require approximately the same services from the platform, there are always going to be those that break this trend or require a platform larger than our upper limit of 250 kilograms. For example, some sort of deep space astronomy missions might be out of our reach at this point. Also, as part of the external inputs phase, the stakeholders who may have an interest and impact on the OSSAT program had to be identified. So this slide shows what we refer to here at KISP as a pig in the middle diagram, and this identifies all of the stakeholders of the OSSAT program and their individual interests in its development. So, for example, here we have operators of the spacecraft, malicious third parties who may look to disrupt the program, and customers of the program as well as a few others. So this identification of stakeholders was conducted after an initial exploration of the wider context within which the open source satellite will reside. And it was through this exploration that we further understood the environment within which the OSSAT may be used. And this has then allowed us to derive this list of stakeholders whose perspectives we would be interested in. So this context examination also meant that we could analyse the various degrees of influence and control we may have over some of these stakeholders. And this diagram is an example of a bit of a model-based systems engineering artifact, and I'll talk a bit more about MBSE later on in the presentation for those of you who aren't aware of it. So having now identified the applications we want the open source satellite to service and the stakeholders we believe have an invested interest in the program, the needs phase aims to identify what is required of the OSSAT program by these various applications. And this included identifying the needs of each of the platform, payload, and ground segments. So we initially developed a set of generic needs for each of the segments, which we believe will cover most of the requirements that specific applications would have of the open source satellite. These were then used to generate a concept operations, a template, which would be used to identify what individual applications require from the platform and ground, and what the operations of these types of missions involve. So the main aim of generating these CONOPs documents for each of the applications is to better understand what the different types of payload require from the platform segments to allow them to operate. So we've developed CONOPs for those applications that we have sort of personal experience in, and we've then had discussions with external parties who have experience in perhaps different fields to ensure that we've fully understood what the OSSAT would need to be able to offer to fly those types of payloads. And we've also made use of the experience of some of your collaborators by asking a few of you to generate these documents for the program. So this phase has also included engagement with stakeholders such as satellite operators, missions, or even insurance providers to understand how the needs of these people may impact the architecture. So this is an activity we are actively engaged in at the moment, as well as continuing to generate those CONOPs to identify those platform needs. And this figure is just an activity diagram showing a generic set of satellite operations. And this goes right from integration and test all the way through to decommissioning. And so we believe that from a top level, most spacecraft will go through this sort of life cycle. And the idea of generating these CONOPs documents is we will refine this to get to one for the open source satellite platform that will cover all of these other applications. So I thought it'd be a good idea to give you a quick example of some of the CONOPs that we've generated, and this one is for an Internet of Things application. So Internet of Things, or IoT, is as a space application, is about providing connectivity to devices in remote locations that would otherwise not be able to be connected to the internet. So in terms of a small satellite Internet of Things mission, this is normally aimed at relaying data from small, low-power sensors in remote locations to ground stations where the data can then be uploaded to a network and the user can then access it. So this allows sort of near real-time updates of systems in isolated parts of the world. So by generating a concept operations for Internet of Things, we've been able to understand what such an application would require from the satellite platform. We've learned that the payloads themselves are receivers, typically operating in an ultra frequency band, and they do not require a lot of power from the platform, approximately less than 10 watts for normal operation, and that the payload itself is generally on for the entire mission. So we've also determined that the Internet of Things payloads do not have a high pointing accuracy requirement, and that the amount of data that must be stored and downlinked to the ground is relatively low, especially when compared to an Earth observation mission, for example, taking images of the ground. So it is details like this and the specifics of these details that we're going to use to ensure that the OSSAT platform will be capable of servicing an Internet of Things mission. So through this research, we've determined that Internet of Things in particular is not a highly demanding application, but it also has features that we will need to consider during the design of the platform architecture. One of these being the requirement that an IoT payload will generally need a low noise environment to operate, as they need to be highly sensitive to detect signals transmitted from devices on the ground. It's also very likely that an IoT application of the OSSAT would operate within a constellation. So most IoT providers are currently planning on using inter-satellite links to reduce the time between receiving data from a device and transferring that to a user. So it turns out actually that a few different applications might require inter-satellite links, and therefore we are now in the process of considering whether maybe that should be something that is part of a standard platform, or maybe an additional unit which could be bolted on depending on the application. So that's just one example of the sort of decisions that we need these. So on the right here, we have a diagram which shows a typical mission architecture for an Internet of Things application. And this just gives you an overview of some of the interactions of the satellite with ground stations, and the infrastructure that is needed to successfully operate one of these missions. So we've recently made our IoT CONOPs open source, and those of you who have access to our systems Teams channels will now be able to view it. And perhaps we could also move it over to the other Teams channels we have so that everyone can view the document if they wish. So another example of one of the CONOPs, this is a synthetic aperture radar mission, and this provides a nice contrast to the Internet of Things application. As opposed to IoT, SAR has a number of features which make it a fairly demanding application to fly satellite platform. So synthetic aperture radar is a remote sensing technique which can generate really high resolution images of ground targets and can allow the determination of characteristics of a location that a normal image cannot. So a SAR payload works by transmitting, in the case of small satellites, microwaves at the ground, and these are then reflected and received by the payload. And then the amplitude and phase of these reflected signals can then provide information which is used to construct the images. So the most sort of drastic requirement of a SAR payload, as you can see on the slide, is its power consumption. So when operating, a small satellite SAR payload could well require around 1,000 watts of power. And this is why SAR has only recently become an application that a small satellite can even service. But even so, this level of power requirement means that a SAR mission can generally only image for around 5 minutes per orbit before needing to recharge its batteries again. So with such a variation in power requirements between applications, remembering that the IoT payloads only needed around 10 watts, one of the key projects for the OSSAT program is going to be the development of a modular power system, which can account for such a variation in power generation and storage needs. So also, as with any high-resolution imaging payload, when the satellite is imaging, it needs to provide a highly stable pointing so that it can accurately detect the reflected microwaves. And also, due to the inefficiency of a radar chain used in a payload such as this, the majority of the power required by the payload is actually converted to heat, which must then be removed from the spacecraft in some way. And this would pose an interesting thermal design challenge and also a challenge for the design of the structure of the platform, because upwards of 500 watts of heat could be generated during imaging. So SAR is a good example of the challenge we've all taken on to try and design a platform that can service something like an Internet of Things mission, as well as an application as demanding as SAR. And again, developing the CONOPs for this has highlighted a number of factors that we will need to consider as we head towards designing that physical architecture of the system. So hopefully that gives you a bit of an overview of some of the key requirements of a couple of these applications, and what we can do is in the future we could perhaps do some more focused presentations on specific phases, and if people would like that, we can provide some more information on the other CONOPs we've generated. So the systems team, we're currently in the needs phase of the OSSAT development, and we're still working on generating CONOPs and engaging stakeholders so that we can better understand what the open source satellite should be able to do to meet the objectives we've set for the program. So just to give you a bit of a brief overview now on what the future work looks like after we've completed the needs phase. So at this point, we will have considered what each of our down-selected applications requires from the platform and ground segment in order to operate, and the viewpoints and interests that other stakeholders have in the program. So from this, we'll then have consolidated the generic set of needs we developed to ensure that they satisfy the needs of the specific applications and stakeholders. So this would lead to what we're calling the functions phase and then the features phase. So in the functions phase, we will determine how we're going to realize the needs of the different applications derived in the previous phase. So these needs are going to then be broken down depending whether they are applicable to the platform, payload, or ground segment. And then we'll be able to derive a top level set of requirements for each of these systems. And then moving on to what we deem the features phase. And this will involve really understanding what's going to make the platform and which of those functions should be sort of kept within the platform. So the top level requirements derived in the previous phase will then be able to be broken down and grouped so they can be assigned to an individual entity within the platform. And this could be, for example, more specific requirements on the attitude determination and control capabilities of the OSSAT. So we now have sets of requirements that describe what is needed from the major entities within the open source satellite platform. And the aim of this physical architecture phase will be to take these and generate a set of requirements for each component of the system. And this will be an iterative approach. And the idea here is that these requirements could be given to potentially an external party who could go away and design that individual component based on the information we've given in those requirements. So the completion of this phase will, however, leave us with a physical architecture with requirements for each component, and the interfaces between different components will have been defined. And throughout the functions, features, and physical architecture phases, verification of the requirements at each stage will be conducted. So we will use those applications that we defined back in the external inputs phase, and those that we deem to be test cases for the program. So we will run these additional applications through our architecture to see if the design we have come up with is capable of servicing all of the applications that we wanted it to. So I know I mentioned earlier model-based systems engineering, and I thought I'd quickly just describe how we're using this technique in the program. And for those of you who are unfamiliar with MBSE, it is an approach which aims to move away from programs which utilise sort of documents as the primary means of storing information, and moving towards a more model-based representation. With a set of related models which can be used to hold information related to defining requirements or conducting design analysis and verification work. We're using a tool called Enterprise Architect to create this model repository, and this model is going to be used as a single source of truth during the program, and will contain the information related to the context within which the OSSAT resides, all of them needs of the applications and stakeholders, and the functions, features, and eventually physical architecture of the open source satellite. And then when we run test cases, such as those different applications to verify the OSSAT design, we'll also use it to store the results of such verification exploration. So that was a bit of a whistle-stop tour through our sort of systems approach. As I said before, I think that the idea is if people would like it, we can provide more specific and focused presentations on individual phases in the future, perhaps some more information on CONOPs, as I said. But